Alright, so let us next start solvability by radicals. And in this section we are going to see that polynomials of degree 5 or higher do not have any formula using which you can find all their roots. There is no general formula. We are going to investigate this issue and we are going to prove this fact. So to start our discussion, let us consider a specific quadratic polynomial with rational coefficients. This polynomial, x square plus 3x plus 4 over the field of rational numbers q. From the quadratic formula, we know what its roots are. And the roots are, if you just simply use the quadratic formula, minus b plus or minus root b square will be 9 minus 4ac, that means 16 divided by 2a, so 2. That means the roots are minus 3 plus or minus square root of minus 7 divided by 2. Now, obviously you can see that none of these two roots is a rational number. Both of them lie outside the base field Q. However, if you adjoin this number, square root of minus 7, or in other words, square root of 7 times I to the field of rational numbers, then this extension has both the roots. Now the thing to be noted here is that there exists an element gamma, which in this case is minus 7, which however is in the base field, such that if you consider an element omega whose square is that element, that is, which is gamma, and attach that omega to the base field, that is, obtaining this extension, then this extension has all the roots of our polynomial. Now, we are of course not going to consider specific polynomials like this, but we will consider general polynomials. Now, instead of this, when we consider a general polynomial, and that too not over the field of rational numbers necessarily, but over any field actually, let us do that and see what we can say about that. Now, when you consider a general polynomial, there is in fact no need to consider any polynomial, or in other words, it's enough to consider only monic polynomials. That's because if you consider a non-monic polynomial, it does not really add anything to the discussion. If anything, it just unnecessarily increases complexity. So it's enough to consider only monic polynomial. So we consider this general quadratic monic polynomial over f. F is some field. Okay. Now, in order to have a smooth discussion, instead of thinking of this as a general polynomial over f, we can think of it as a particular polynomial over this field. That's because you see the general nature of the polynomial means that a1 and a2, although they are elements of f, but they are not some specific elements of f. They are themselves variables varying over f. So a1 and a2 are just a1 and a2. So what we do, instead of interpreting this as an element of fx, we interpret this as an element of this x, that polynomial ring, where this is the field of rational functions in the indeterminates a1 and a2 over f. You remember the field of rational functions. You first do this. You consider this polynomial ring with two indeterminates. Because this is an integral domain, it has its own field of fractions in which it can be embedded. That is this field. Okay. So basically what we are doing is that we are considering this to be a particular element in the polynomial ring, this x. Alright. Now for this polynomial, of course, also we can use the quadratic formula to get its roots. Now if you do that, I cannot use that part right now. Okay, we are going to need these things. So I have to just erase this, and let me just write down the roots of this polynomial just using the quadratic formula, keeping in mind that here f is just some field. So the two roots will be this, again like before, a1 square minus 4a2 divided by 2. Now these two roots may not belong to f, but of course you can adjoin them to f, obtaining an extension of f in which they will lie. Now note that in the previous specific example you had minus 7 here. In place of minus 7, now we are getting a1 square minus 4a2. So just like the previous case, if you consider, let's just write exactly like what we did there. Let gamma be a1 square minus 4a2, and this of course belongs to this. Do you see the slight difference? If we could have written f here. However, because we are treating a1 and a2 to be general, so that's why we treat this as a rational function in a1 and a2, and as such, this now belongs to the field of rational functions. In fact, this is actually a polynomial function in a1 and a2. Okay. Now, if we can find means if we define omega to be an element such that omega square is this, and attach that omega to this field, and thus obtaining, let me write here, there I don't have space, obtaining this extension, then in this extension both the roots will lie. Alright. And also one more thing that you can note, it is in fact the thing that we should note here about this situation, it is that the roots are expressible as rational functions in the coefficients a1 and a2 the roots involve rational functions in a1 and a2. What else do they involve? They involve addition, multiplication, subtraction, division, all those things in this field, and at the same time, not just that, square roots also. Okay. The square root is needed, otherwise you could have just simply obtained whatever you have here in this field itself, but this is not enough. You have to extend it by including a square root of this rational function to this field, and then that extension contains the roots, And that is why the original roots are expressible as combinations of square roots of rational functions of the coefficients a1 and a2. Now, instead of a quadratic equation, if one, a quadratic polynomial, if one considers a general cubic polynomial, say, and here also, instead of interpreting this as an element in fx, we interpret this as a particular element. Instead of having it as a general element in that ring, we consider it as a particular element in this ring, where just like this one is the field of rational functions in a1, a2 and a3, okay, 3 indeterminates. Then here also one can have a way of getting the roots in terms of coefficients, which is this fairly complicated way. What you first do, you have the coefficients a1, a2 and a3, treat them as indeterminates. You define two new quantities, p, which is a2 minus a1 square divided by 3, and q like that. And then using p and q, you define two further quantities, capital P and capital Q, which involve cube roots of square roots. And it is mentioned in the text that these cube roots are taken appropriately, okay, taken carefully. And then, in terms of all of these, the 3 roots of that original polynomial are this and this, where this omega that you see is not equal to 1 and is itself a cube root of unity, cube root of 1. 1 is also a cube root of 1, but it's not 1, it's any one of the other 2. This is Cardan's method or Cardan's formula. So if you think of an extension in this case like this one, it's not enough to simply attach the square root of this, this square root to this field. You also need to attach a cube root as well. So here you get, in fact, an extension by attaching means adjoining, of course. I need to keep the language correct. Here, adjoining a single element which was a square root was enough. Here you would have to adjoin a square root and then a cube root. Then that extension will contain these 3 roots. And in this case also, you see that the roots are, this time however, cube roots also have to be taken into consideration. Here, the roots are expressible as combinations of square roots and cube roots of rational functions in the indeterminates. Indeterminates means coefficients of the original polynomial. And if one goes to the next higher degree, a polynomial of degree 4, a general polynomial of degree 4, monic of course, then by doing some operations to that polynomial, the problem of finding its roots can be reduced to that of finding the roots of a cube. And there also a similar discussion can be had, which of course it becomes more complicated to actually show how to find the roots. But in that case also, the roots are expressible as a combination of square roots, cube roots, I think 4th root also, I'm not exactly sure, of the coefficients or of rational functions of the coefficients. That's the point. What the actual thing that we have about a 4th degree equation, that's not the point. The fact is that there also you have simply put, you have a formula for the roots. In terms of these coefficients, a1, a2, a3, there you will have another one, a4. because you will be having x to the power 4. Now here's the thing. If one considers general polynomial equations of degree 5 or higher, then such formulas do not exist. Do not exist does not mean that mathematicians haven't been able to find such formulas, but it means that such formulas are impossible to exist. Okay, so let us now continue our discussion next with this consideration. When shall we say, I mean, it's a little, what can I say, a little complicated to express this idea. I mean, it is still somewhat vague. What do you say when you want to express the fact that the roots of a polynomial can be expressed as a formula in terms of the coefficients? How do you express this mathematically? So that is the next idea we are coming to. Okay, so now I can use this part. In other words, when do we say that a polynomial is solvable by radicals? What is the meaning of that? From these examples, we can say this in general. Let f be a field and consider a polynomial px in the ring fx, or a polynomial px over f. We say that px is solvable by radicals over f if we can find a finite number of fields like this: f1, which is obtained by adjoining some element omega 1 to f, the original base field. Then f2, which is obtained by adjoining some other element omega 2 to the previous extension f1, and it goes like this. Eventually, you reach an extension fk, which is obtained by adjoining some element omega k to the previous extension fk minus 1, such that some powers of these elements that have been adjoined belong to those fields where they have been adjoined, such that some omega 1 to the power r1 belongs to f, omega 2 to the power r2 belongs to f1, and like that it goes. And finally, some power of the final element omega k to the power rk belongs to the previous extension fk minus 1, and the final extension fk contains all the roots of px. When this happens, when we can find a finite number of fields like this for which all these things happen, then we say that Px is solvable by radicals over the base field f. For example, a general quadratic polynomial is solvable by radicals. Well, I should not have said a general quadratic polynomial. For example, this one. Okay, let us take that example itself. This is a polynomial in Qx, right? Now we have found finitely many fields. In fact, we have just found one field itself that was enough for our purpose, which is f1, and f1 is this. You see, that means this is our omega 1, such that this extension itself, you can imagine f1 in place of fk. In the very first step, our job is done. That's because this field there contains both the roots of our polynomial. Not one more thing, that okay, what about these things though? What about this? In this case, that R1 is 2 because this is minus 7 and that belongs to the base field. For some other polynomial, you may have to do 2 steps or 3 steps, but does not matter how many steps you need. If you eventually get to a field like this, satisfying all these things, which contains all the roots of your polynomial Px, then you say that okay, Px is solvable by radicals over the original field over which it's a polynomial, that is f. Okay, so that's how we express solvability. It is not something that can be done at once, but it is done in steps, a finite number of steps, but how many, that depends on the situation. Okay, so let us next consider this. If k, with this px and everything, if k is the splitting field of Px. Of course, every polynomial will have a splitting field over x. Over f. Then Px is solvable by radicals over f if such fields, if a finite number of fields as above, that means with these properties, can be found such that k is contained in the in the final field fk. That's because a splitting field by definition contains all the roots of our polynomial whose splitting field it is, and at the same time it's the smallest extension, so that's why it's the extension having the smallest possible degree. And then the author has made a remark and mentions, says that this remark will be used in some of the proofs of some results that we are going to see in this section. And the remark is that if such an fk can be found, oh, I should have written fk. Doesn't really matter what I write here, but I said as above, no? So we should respect this. Okay, so the remark says that if such an fk can be found, then one can assume without loss of generality that this fk is a normal extension of the base field f. But exactly why is that true? That is exercise 1 of this section. So we will see there itself while solving the exercise why one can make this assumption without losing generality. Fk after all is going to be an extension of f, right? Because extending f you get f1, extending that you get f2. So finally you are getting fk, so ultimately fk is an extension of f, but we can assume that fk is a normal extension. Alright, next, by a general polynomial of degree n over f, i.e. px equal to n minus 1, so on up to n, we mean the following. Consider the field of rational functions in these indeterminates over f. We consider that px to be a particular polynomial over this. Particular polynomial over that field or in this ring. Okay. And we will also say that this px is solvable by radicals. You see, there is a slight difference between considering a particular polynomial over f, the kind of polynomial we considered at the beginning of our discussion, that is a specific polynomial x cube plus, or x square plus 3x plus 4. That's a specific particular polynomial. That is a polynomial over the field of rational numbers. However, when you consider a general polynomial like this, where the coefficients themselves are varying, their parameters are unknowns, then instead of thinking of it as a polynomial over, say, over f, you again consider this as a particular polynomial over this field of rational functions. And when we say that such a polynomial is solvable by radicals, what do we mean by that? We say Px is solvable by radicals if Px is solvable by radicals over that field. And the meaning of this is already known. Solvability of this polynomial over this field means again finding a finite number of extensions of this by adjoining more and more elements successively to the extensions themselves, such that all those other conditions are true. Okay, so this is what we will mean. First of all, if we are given a general polynomial like this of any degree, then we consider it to be a particular polynomial over the field of rational functions in its coefficients. And then, considering that as a particular polynomial, whatever we do with a specific polynomial will be done to Px. For example, Px will be called solvable by radicals if it is solvable by radicals over this field. And this thing really expresses the intuitive idea of finding a formula for the roots of this polynomial in terms of coefficients, its coefficients and combinations of nth roots of rational functions of the coefficients, that discussion that we had about cubic polynomial, that in general can be made mathematically precise like this. Yeah, and then the author says for n equal to 2, 3 and 4, we pointed out that it can always be done. That is, the general polynomials of degree 2, 3 and 4 are always solvable by radicals in this sense. However, let me just write for n equal to 2, 3 and 4, we have already pointed out how Px is solvable by radicals. But for n greater than or equal to 5, Abel proved after whom the notion of abelian group has been named. Okay. Abel proved that Px is not solvable by radicals. That means the general polynomial of degree 5 or 6 or any higher degree is not, it's impossible that it can be solvable by radicals. No, it is not solvable, and that fact was proved by Abel. However, note one very specific thing here. Although the general polynomials of degree 5 or higher are not solvable by radicals, but a particular polynomial that is given to you with actual specific coefficients, say 5 or 3 or something, even if such a polynomial has degree at least 5, that may be solvable by radicals. And in fact, in this text, the author says that we are going to develop criterions for when such a polynomial is solvable by radicals in terms of its Galba group. Alright. Now, in order to go to the results, we are going to need some notions from group theory, which is not there in the main body of group theory in this text. Actually, there are some exercises which I left out at the end of the second chapter on groups. These are the supplementary exercises. There, some of these ideas have been developed, not fully, but maybe as examples or something like that. So, one such idea is the notion of solvable groups. So, we are going to need this. So, that is the next definition. We are going to see this definition and we will stop for tonight here, because there are many more things ahead. We have to only take chunks from them and do one chunk at a time. Otherwise, we will get bewildered by all these things. But anyway, let's see the definition of solvable groups. A group G is said to be a solvable group if there exists a finite chain of subgroups like this. The first subgroup is G itself, and then we have N1, N2, and it goes like this. Eventually, we reach Nk, and that last subgroup is the trivial group, such that there are other conditions also. Such that each subgroup Ni is normal in the previous group of the chain, Ni minus 1, with the understanding, of course, that the least value of I is 1. I mean, if you consider N naught, it does not have a previous group, right? So we are talking about these groups. For each such group, it's a subgroup in the previous group, but it's a normal subgroup. For example, N1 is normal in N naught, N2 is normal in N1, and so on. That's what we are saying here. And the quotient, so if it is normal, you can form the quotient of Ni minus 1 by the normal subgroup Ni. Each such quotient is abelian. If such a chain of subgroups can be found, then we say that G is a solvable group. You can perhaps understand the reason for having this kind of name. On one hand, we are saying solvability of a polynomial by radicals. On the other hand, we are also saying a solvable group. So this will be linked, and we are going to see this link when we dive deeper into this subject. Now, before I end the video though, let me just say something about this word chain. You may have seen this word thrown here and there casually, but don't simply use this word casually in mathematics. It has a very specific meaning. Okay. Let me just briefly say what a partially ordered set is. Partially ordered set, or in short, poset. Suppose you have a set A and a binary relation some star on A, which means that star relates or does not relate any two elements of A. That's what binary relations do. For example, you have binary operations in a group. Well, I should not have perhaps said binary operation, but for example, in the set of real numbers, you have the binary relation less than or equal to, something like that. Such a relation is said to be a partial ordering relation or a partial order if it has three properties. Number one, reflexivity. And you perhaps already know what reflexivity, of course you know, because we have seen equivalence relations, right, in this book itself. It says that A is, instead of writing like this, let me just simply write this itself, with the understanding that this is not ordinary less than or equal to, it's just a symbol, because the set A may not have numbers in it. A is related to itself for every A in A. That is your reflexivity. Number two, transitivity. There is in fact no strict order in which you should write down these things. Okay. I am just simply writing the ones which are familiar to us. If A, B and C are three elements of A and A is related to B and B is related to C, then A is related to C. So that is your usual transitivity. And there is another one which is not symmetry but antisymmetry. What this one says is that for any two elements A and B in A, if A is related to B and B is related to A, then A must be equal to B. If a relationship satisfies these three properties, then it's called a partial order relation or a partial order on the set on which it is defined. And a set along with a partial order defined on it, that pair is called a partially ordered set or a poset. Now, the crucial difference between a partial order and the kind of order that we have on, for example, the system of real numbers is totality. A partial order is not necessarily a total order. What is totality? Totality means that any two elements of your ordered set are comparable to each other. In other words, say you have this partially ordered set and you take arbitrarily A and B in A. Then there is no reason to have either this or this. You may have neither of them true for a specific choice of A and B. One easy example is, for instance, you consider the set of natural numbers, okay. You then have its power set. So in this set you have all the subsets of n. Think of P of n in place of A. And what is this relation? This relation is your ordinary subset relation. Is the subset relation reflexive? Yes. Every set is a subset of itself. Is it transitive? Yes. If A is a subset of B and B is a subset of C, then A is also a subset of C. Is it antisymmetric? Yes. If A is a subset of B and B is a subset of A, then they have to be equal. So that means this is a partially ordered set. In a similar manner, the ordinary set of real numbers along with this ordinary ordered relation is also a partial order. I mean a partially ordered set. But the difference between these two is that if you take any two real numbers A and B, either A is less than or equal to B or B is less than or equal to A. That means they are related to each other in one of the two possible ways. However, that is not the case here. For example, if you consider the subset of even natural numbers and the subset of odd natural numbers, are they related by this relation? Is the set of even natural numbers a subset of the set of odd natural numbers? No. Is this true? No. That is also not true. So that means in a general partially ordered set, two elements need not be related by the ordered relation. That is not the case in a totally ordered set. Okay. Now, although we lack comparability or totality of the order in a partially ordered set, but you may get a subset of this set in which any two elements are related to each other. I mean, if you say get rid of this kind of non-comparability by restricting your attention to some particular, maybe some small subsets of n, within that subset, within that collection of subsets, maybe any two subsets are related to each other. Either this is a subset of this or that is a subset of this. When you have a totally ordered subcollection of a partially ordered set, such a subcollection is called a chain. And the word was used there because we considered those subgroups in that fashion. It's a decreasing finite sequence of subgroups where if you follow those ordered relations, I mean there also you can see that we have used the subset relation. Then any two of them, you take one of them will be a subset of the other. So that is why it is called a chain. Okay, and with this I am going to stop. Tomorrow we are going to go back to set theory from class 11. Okay, so tomorrow we will see a video, and as well as we are going to see exercise solutions. So that's just it. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.